Okay, notes for today, geometric probability. Pretty sure you guys are familiar with some probability already. Our central question is, what are the similarities and differences between geometric probability and the probability of rolling a 4 on a regular die? So here's a die. Yeah, because how many 4s are on this die? There's only one, and how many sides are on it? There are 6 faces, so 1 out of 6, exactly. Okay? Now here I have 52 cards. Oh, I meant to have you give me the number. I gave it away. 52 cards. I took the jokes out. The jokers out. You know, I know a couple of magic tricks, but I usually do them at the end of the year. When we have time to burn. This is crunch time. 52 cards here of regular face cards. So, in case you're not aware of the face cards, there are 4 suits. What are the suits? Hearts and diamonds, spades, and clubs. Exactly. And there's 13 cards of each, starting with ace all the way up through king. Ace, 1, 2, 3, 4, all the way up to 10, jack, queen, king. Okay, so, Benito, out of my deck here, what's the probability that I would draw a 3 of, oh, is that a club? 3 of clubs. 1 out of 52. Great. What's the probability? You can tell me the probability that I would just draw a 3. 4 out of 52, which simplifies to...
Oh, 1 out of 13.
1 out of 13. Yep, 1 out of 13. Okay? Ooh, here's a fun one. What's the probability that I will not draw a king? So drawing a king and not drawing a king, if you put that word not, that's called the complement, so it's everything opposite. Yeah, 12 out of 13. Because if there are 4 kings, right? So 52 minus 4 leaves us with how much? 48. 48 out of 52 of these are not kings. And if you simplify it, it would give you 12 out of 13. Okay, so that's regular probability that, actually it's called theoretical probability that you guys are aware of. Theoretical probability where the math backs it up, because assuming that dice is actually fair, you're probably rolling a 4. Like you mentioned, is 1 out of 6. Okay, so rolling a 4 is called the event. The 1 is called the number of favorable, because on the dice, there's only one side that has a 4. Number of favorable outcomes. And on a dice, there are 6 possible outcomes, right? There's 6 different sides on the dice. So the denominator is number of total possible outcomes. Okay. So geometric probability essentially follows the same outline. The numerator is the partial amount. There's only one side on this whole die that has a 4, so that's a partial amount. The denominator is always the total. There are 6 total sides on this die. 1 out of 6. Partial divided by total. If you can remember that, partial divided by total, then geometric probability will be simple for you, because it's the same thing. Okay, so geometric probability the definition, thank you, is it's the ratio that involves geometric measures such as length and area. Because in geometry we use a lot of shapes, right? Like triangles and circles and line segments. So measuring one-dimensionally, that would be length. Two-dimensionally would be area. So ratio involving geometric measures such as length or area. Oh, was this from Adam?
No.
Amber, okay. All right, example 1. We're going to do a probability problem off of length. So we're given a picture, which is just a line segment with endpoints A and D, and in between we have points B and C. We want to find the probability that a point S, is there an S on that line segment right now? Is there an S on the line segment? No. So we want to find the probability that a point S will be randomly placed on BC. On. Bless you. You okay? What's the probability that we'll randomly place a point S somewhere on the segment, and what's the probability that it will actually land on BC? So, remember, probability of the event essentially is the partial divided by the total, or the whole. Okay, this one's going to be a little abstract because there aren't actually numbers. There aren't actually numbers. And you don't actually know if each of those points are evenly spaced. You don't know that. What you do know is the partial. We were asked to see if it would randomly fall on which segment? BC. So that's the partial. Divided by the total. What's the total segment? AD. Okay, the next one will actually plug in some numbers with the segment, but we don't have numeric values. That's our probability. Probability that it will randomly be placed on BC is BC divided by the total. Does that make sense? Partial divided by total. You guys are tired this morning. Okay, let's try another one. This will also have a segment, but it will have numbers, so for heads it will make more sense. Okay, so here we have a segment. Starting with 2, all the way up to 14. And we're going to be counting by 2s. 2, 4, 6, 8, 10, 12, 14. We're given that we have a point S on 2, point Q on 5, point R on 8, and 14 is T. All right, would someone like to give me a letter that's not listed right there? Any letter? Any letter? M?
E.
E. Okay. What's the probability that we would randomly place a point E, what's the probability it will land? E will land on, we'll put randomly, land on QR. Okay, so let's talk about the segments before we get into the numbers. What's the partial segment? Excellent. QR. Over the total, S to T. Any questions on that? QR is the partial we're looking for. Divided by the total from end to end is ST. Now we actually this time have numbers. Show me your fingers in the air, please. How long is QR? What's the length of QR? Fingers in the air, please. What's the length of QR? Oh, guys, it's not 3. Look again. Oh, I lied. I'm sorry. I was thinking 5. So that Q is on 5. That's where the 5 came from. You guys are right. It is 3. Okay, let's try this again. Oh, we don't have enough fingers for this one. Amy, how long is ST? What? Good. How come it's not 14, guys? Yeah, it doesn't start at 0, does it? It starts at 2. So 3 to 12. Noah, I believe this simplifies. Can you tell me what it would simplify to? What number divides into 3 and 12? Not quite. What number can we divide into 12 that also divides into 3? There you go, because we can divide what number? 3. Divide by 3, divide by 3, and so we get 1/4. Now, probabilities can actually be written in 3 ways. We can write them as fraction form, decimal form, or percent form. Generally, percents actually make a little more sense in our head. What is 1/4 as a percent? Good. So we have a 25% chance that if we randomly placed a point on the segment, it would end up on the segment QR. 25% chance. So what's the probability that it will not land on QR? Excellent. So that's the complement. 75%. Is this making sense now? Now that we threw numbers in it? Daddy, can I get your note, please?
It's not a note.
The tardy ticket?
Yes.
Yeah, can I get it, please? So I can remember who's coming in late. Thank you. All right, next problem. A commuter train runs every 25 minutes. A commuter train runs every 25 minutes. Commuter train would be like a train you would take to work. You do that a lot. Like in,
New York?
well, New York you take the subway, but I guess you could call it a train. Yeah.
You did a lot.
Tracks is not really a train. It's a light rail train. So yeah, kind of. It's a weak version of a train. But like New Zealand, they take trains to work. When I went to Peru a couple years ago, we rode a train from Cusco into Machu Picchu village, and I was like, I'd only been on, besides tracks, which isn't really a train, I'd only been on the Heber Creeper. Has anyone been on the Heber Creeper? Yeah, it's this like old train out in Heber past Park City, and they like have it decorated like old-fashioned times, you know. And I rode it once for my birthday when I was like 10 or 12, something like that. And it's really slow. That's why it's nicknamed the Heber Creeper. But so the only other time I'd really been on a train was a couple years ago when I went to Peru. And I was like, oh my gosh, this is so cool, because they had like Class A, they had Class B, Class C, kind of like old-fashioned times, or someone said yesterday Harry Potter times. They have different classes on the train. And most people in my group were actually from New Zealand or Australia, and they ride a train every day to work. So it's not something new and exciting for them. So that's a commuter train is what they take to work. Okay, anyway, the commuter train runs every 25 minutes. If a commuter arrives at a station at a random time, if a commuter arrives at the station at a random time, so maybe they don't know the schedule and they just show up whenever they show up. What's the probability that they will wait for at least 10 minutes? But the train is only going to show up every 25 minutes on the dot. They're very precise with their schedule. If a commuter arrives at a station at a random time, what's the probability that they will wait at least 10 minutes? Can we give a visual aid like we did on the last two problems that would match the situation? Yeah. What can we draw? A train, okay. What else can we draw? Adam, please take the earbud out of your ear. Thank you. Do we have some number values that we could...
25.
Okay, what is 25 representing? Minutes, and what's the lowest number? No. 0. Okay, so I can't draw a train. Okay, there's the front of my train. Okay, smoke coming out. Train A has just taken off at 0. Train B will come 25 minutes later. So there's space in between. Who wants to draw 25 lines between? Anyone? Not me. What can we count by instead? 5. So that would be a good choice. Okay, so say you arrive right when that train A is taking off. How long are you going to have to wait till train B is ready to go? 25 minutes. What if you arrive... Oh, I forgot the 20. Whoops. Whoops. Oh, that's better. What if you arrive at 20 minutes after train A takes off? How long are you going to have to wait? 5 minutes. Okay, so we want to know at least 10 minutes. So actually, let's figure out, when would you wait exactly 10 minutes? Do you agree with that? 15, right? At 15, you would wait exactly 10 minutes. How long are you going to wait at 14 minutes? 11 minutes. And 10 minutes, you'd be waiting 15. So essentially, anything from that train A taking off right at time 0 all the way to 15, will you be waiting at least 10 minutes? Yeah, either exactly 10 minutes or more. Okay, so there's our line segment. Let's find the probability that you're going to wait for at least 10 minutes. X is greater than or equal to 10. Or maybe we can even put M for minutes. Minutes is greater than or equal to 10. Partial divided by whole. Cassie, please put that away. Okay, admin, what's the partial length? Good, 15. Divided by the whole, Forrest. 25. Okay, Christian, would this simplify? They're both multiples of 5. Is there a number that divides into 15 and 25? Yeah. What is 15 divided by 5, Christian? What's 15 divided by 5? And 25 divided by 5? 5, 10, 15, 20. What? Yeah, good. So, 3/5, or let's see that as a percentage so we can actually wrap our heads around what 3/5 means. 60%, thanks. So you have, if you show up randomly, or a commuter shows up randomly, you have a 60% chance to wait at least 10 minutes. What's your chance of waiting less than, your probability of waiting less than 10 minutes? 40%, excellent. Okay, so we've done 3 length problems. Are there any questions on how you find the probability using the length? Okay, good. Let's try area, because geometric probability also goes 2-dimensionally. Okay. probability and area. Okay, it's basically the same idea, except for it's going to be two-dimensional. So this segment above, A to B, is just one-dimensional because it only has one direction. But if we give a two-dimensional figure, such as this figure P, and the second one, N, the probability that you drop a random point would be, again, partial divided by whole. So say we did the probability of, Gentry, give me a letter, please, that's not P or N. Okay? A. Okay, the probability that A is randomly placed on N. That would be the area of, what's the partial?
A.
D? Keep your eyes open, please. What's the partial? What's the partial shape?
A.
Area. No, A is a point randomly going to be placed on what? N. Area of N divided by, what's the total? Area of?
P.
Good. Okay? So it's the same idea. So on our example 4, even though it's two-dimensional now, it will apply the same idea of partial divided by total. Okay, a circle is inscribed in a square. A circle is inscribed in a square. Now, I briefly threw out the word inscribed last time in our notes. Circumscribed is it would be outside the shape, and it would touch the shape only at the vertices. Inscribed would mean it would be where?
Inside.
Inside the shape. Okay, a circle is inscribed in a square. Point P in the square is chosen at random. Point P in the square is chosen at random. I hope you've noticed that the key common word in all of these has been random. Randomly placed. What's the probability that Q lies on the shaded region? So I'll have to draw you the picture here in just a sec. What's the probability that Q is on the shaded region? Oops. Okay, here is the picture. Square. To mark that it's actually a square, we know in a square all four sides are congruent, correct? And we know all four angles are congruent, is that right? Okay, so an inscribed circle is actually, with a square, is actually going to touch exactly 4 times, because the square has 4 sides, and it will actually touch at the midpoint of each side. And our shaded region is going to be the region outside the circle, but still in the square. Yeah, you need to know where the shaded part is. And we're given that the side length is 6 centimeters. Okay, so what's the probability that a point Q is randomly placed and it lands on the shaded region? Okay, this time we're dealing with areas, not just length, so we can't just say, oh, that square is 6 long, but that's not how you say the measurement of squares. We say the measurement of squares in area, right? Yes, area. Okay, does anyone remember the formula for the area of a square or a rectangle? Would be the same. Base times height, length times width, right? So the area of a square is base times height or length times width. Okay, Danny, what would our area be for this square?
Would it be 36?
Because 6.
6 times 6.
Yep. And then technically we would do centimeters squared. Okay, are there other shapes here we can find the area of to help us solve the partial divided by the total? Yeah, the area of a circle. Who remembers that formula? Area of a circle. Okay, Danny?
Like, we have like the circumference.
Circumference is different. That's just the outside.
Oh.
We want everything inside. Arbor? Yep. So the way I remember, because people get confused, 2 pi r and pi r squared. The one with the squared is area, because area is like a centimeter squared. Pi r squared. So, pi times the radius squared. Check out the circle, please. Put up the radius with fingers in the air. How long is the radius? Fingers in the air. How long is the radius? Good. 3, right? Why is it not 6? Ah, that's the diameter. 3 just goes from here to here. Right? So this would be 9 pi. And for right now, I'm going to keep the pi in, and then once we type in our calculator, we can use the pi button, and it will handle the decimal for us. Okay, so the probability of Q being on the shaded area needs to be the area of the shaded region divided by the area of the total, because the area of the shaded is the partial. How do we find the area of the shaded region? What? Yeah, starting with, which one is on the outside of the larger part? 36. And you subtract the smaller, which is the circle, 9 pi. And that would give us the area of the shaded. It will give us, because these kind of look like triangles, but they're not really because they're curved. So you have to take the area of the whole. Dee, sit up, put your bag down so you're not using it as a pillow. Area of the whole, subtract out the circle, and it will leave these little orange shaded sections. Yes? I never thought about that. I want to see why it wouldn't be. Mind blown. Alright, so now let's find the probability. Probability that, I think we said Q, yep. Q is on the shaded. What is the area of the partial, which is only the shaded section? No, 9 pi is just the circle. What's the area of the partial area, which is the shaded area only? Yeah, it's all of this. 36 minus 9 pi. Divided by area of the whole. Eric, what would the area of the whole be? The whole square. 36. Okay? Looks like a bunch of people still need to get calculators. Let's pick up calculators. Since the directions say use 3.14, we don't use 3.14 unless directions say to. So we're actually using the pi button. Also notice the numerator I put in parentheses because we have to let the calculator know that both of those belong in the numerator. Please put 36 minus 9 pi in the numerator. Type it in. The quantity 36 minus 9 pi divided by 36. Chibs, let me know when you have your probability. That's a decimal. 0.21, round correctly, what would come after the 1? 5. Which is what percentage? Yep, 21.5%. Chance that if a point is randomly placed, it will land in the shaded area. What's the probability that will land in the circle, not the shaded area? 78.5%. Yep. Okay. All right, one more just to make sure you guys get the area idea. This time we have a triangle inscribed in, a triangle inscribed in a square. What's the probability that a point R will land on the shaded again? And the shaded portion is outside the triangle, both sides. Okay, and we know this outside length is 5 inches. So probability of R being landing on a shaded area, if one placed randomly, is area of the partial divided by area of the total. So what shape is the partial? Triangle. So we need to know the area formula for a triangle. Okay. Nathan, do you know the area formula of a triangle? Good. 1/2 base times height. You could also say base times height divided by 2. That would be the same. Okay, Anna, what is the base of this triangle? Just 5. And what is the height of the triangle, Anna? What's the height of the triangle? 5. Good. So, 5 times 5 is 25 divided by 2. What's the area? Half of 25 is 12.5 inches squared. Okay, so we have our the area of that triangle. What's the area of the square? 25. Oh, square. Length times width, or base times height. 5 times 5 is 25. Okay, so to find the probability of R being on the shaded region, we need to do the area of the shaded divided by the total. Yes? Maybe. Okay, but what's the area of the shaded region, knowing that the area of the unshaded triangle is 12.5? And the total is 25. Like we did before, 25 minus 12.5 gives us, okay, so 12.5 divided by the area of the total. What's the area of the total? 25. And that simplifies to what Stiles noticed right off the bat. What's 12.5 divided by 25? 0.5, which is 1/2, or 50%. Okay? Which means there's also a 50% chance it lands in the white triangle. Any questions? Heather's not here, right? Who else here? Okay, so the assignment that goes with this is in the book. Begins on page 582. Numbers 1 through 15.